In the previous lesson, you learned how to create Lewis structures and learned about all of the exceptions that are involved with Lewis structures. Now we're going to use that knowledge in order to then be able to determine how molecules actually look, to determine the geometry of these molecules in order to better predict how they're going to react in reactions. In order to do that, in order to determine their geometries, we need to talk about the Vesper model. But in order to do that, I need to clarify a couple of definitions. Electron domains are areas where you're most likely going to find electrons. Now, there are two different types of electron domains. There's the bonding pair, which is the region where electrons in a single covalent bond are most likely to be found. So those are the electrons that are being shared between two atoms. And they're the non-bonding pair, which is the region around one atom where electrons are most likely to be found. Those are the lone pairs of electrons. Now, when I'm talking about the total number of electron domains that an atom has, you take the sum of the number of bonding pairs and the number of non-bonding pairs. And we'll look at that in just one second. Now, the Vesper model states that the best arrangement of a given number of electron domains is the one that minimizes the repulsions among them. What you need to keep in mind is the fact that the atoms and the non-bonding electrons, they repel one another because they have the same charge. They have a negative charge. And so as a result, what the Vesper model tells us is that the geometry that your Lewis structure is going to assume is going to try and minimize the repulsions that are occurring between the atoms and their electrons and the lone pairs of electrons. And that'll become really evident in just a second. This is just looking at the number of electron domains. So for example, if I have two electron domains, okay, my shape is going to be linear, and the angle, as you can see, the angle between the two atoms is going to be 180 degrees. Now, if I have three electron domains, the shape, the electron domain geometry that is taken is trigonal planar. Now, if you notice, there are three purple lobes here, so the angle between each of these is going to be 120 degrees. If I have four electron domains, the shape that's going to be assumed is tetrahedral, and the bond angles are 109.5. If I have an exception, which remember this is having more than an octet surrounding a central atom, so let's say I have 5 electron domains, which would be an exception, then the shape is going to be trigonal bipyramidal. Notice I've got 3 lobes that are in one plane, horizontal, and then I've got 2 vertical lobes. Notice the angle between one vertical lobe and one of the lobes that's in the plane is 90 degrees, while the angle between the lobes that are in the same plane is the 120 that we had seen above. If I have 6 electron domains, then the electron domain geometry would be octahedral. So let's look at what happens when I change the number of non-bonding or bonding pairs. So if you look right here, if I have 2 electron domains, okay, and I have 2 bonding domains, what that means is I have 2 atoms that are going to be bound to the central atom, then the molecular geometry, which is the geometry of the molecule that you would observe, would be linear. So an example of this would be CO2. Notice I don't have any non-bonding domains. All of them are bonding, and therefore my shape is linear. If you look at 3 electron domains, there are 2 different options that can happen. I can have 3 bonding domains, which means 3 atoms bound to my central atom, okay, and no non-bonding domains. So this example would be BF3. Remember, this is an exception because boron does not have a perfect octet. Notice that the molecular geometry is the trigonal planar that we looked at before, so the angle is going to be 120 degrees between each of these atoms. If instead I have 2 bonding domains, meaning 2 atoms coming off of the central atom, and 1 non-bonding domain, meaning 1 pair of unshared electrons, as you can see, the shape is going to be bent. So one example of this would be NO2 with a -1 charge. Now, if I have 4 electron domains, that increases the different possibilities for what I can have. So if I have 4 bonding domains, then you have the traditional tetrahedral molecular geometry. Now, if I only have 3 atoms bound to the central atom and I have 1 lone pair of electrons, keep in mind 3 plus 1, I still have 4 electron domains, then the molecular geometry, the shape of the molecule, is going to be trigonal pyramidal. If I have two bonding domains, meaning two atoms bound to my central atom, and two non-bonding domains, meaning two pairs of unshared electrons, as you can see below, then your shape is going to be bent. And this example is the example of water, H2O. If we look at the 5 electron domains, if I have five bonding domains and no non-bonding domains, meaning 5 atoms bound to my central atom, then the shape is going to be trigonal bipyramidal. Just, you can look through these, I don't have to read all of these. If I have 4 atoms, that means I have 1 pair of unshared electrons, and the shape is seesaw. Right? Imagine it's a little seesaw. If you have 3 atoms and 2 non-bonding pairs of electrons, then it's T-shape. If I only have 2 bonding domains, 2 atoms bound to my central atom, and 3 non-bonding, 3 lone pairs of electrons, then my shape is linear. Finally, if you have 6 electron domains, so if I have 6 bonding domains, so 6 atoms coming off, then I have the shape of octahedral. If I have 5 bonding domains and 1 non-bonding, then I have square pyramidal. And finally, if I have 4 atoms coming off of it and 2 lone pairs of electrons, then I have the shape of square planar. Okay, so I'm going to give you plenty of practice in order to identify all of these shapes. Some of them, yes, you're going to have to memorize, especially the ones on this page, but as you'll see, they keep repeating each other and you get comfortable with the names. When we looked previously at the electron domains and we looked at the bonding angles that were involved, we saw the 180 degrees, the 120, the 109.5, but what we have to think about is the fact that we've now been adding non-bonding electrons, and we also have the possibility of having double and triple bonds. So how does that affect the angles that we talked about before? If I have 4 electron domains, but only 3 of them are bonding, meaning I have 1 non-bonding pair, would the angle still be 109.5, or does it change? And so that's what we're going to look at right now. So for non-bonding electrons, if I have non-bonding electrons, as you can see from this example, CH4 is your tetrahedral molecular geometry. It has an angle of 109.5, which we predicted. Now, if I still have 4 electron domains, however, one of them is non-bonding, notice that the angle, the bond angle, actually decreases. And then if I have 2 non-bonding domains, the angle decreases even further. So why exactly does that happen? Well, the electron domains for non-bonding electron pairs, they exert greater repulsive forces on the adjacent electron domains. As you can see, they're pushing, for example, in the middle one, those non-bonding electrons are pushing the hydrogens down further so that the angle between hydrogens has decreased, so it compresses the bond angles. Now this is because when you have non-bonding pairs, they're only being attracted to one nucleus. So for example, the non-bonding pair on nitrogen are only attracted to nitrogen's nucleus. When you have bonding pairs, they are attracted to both of the atoms. So for example, between nitrogen and hydrogen, those electrons are being attracted to both nitrogen's nucleus and hydrogen's nucleus. And so as a result, the electrons are not as spread out, and so they don't cause the electron domains to be compressed as much as non-bonding pairs. Just think of it as a fat balloon pushing down the hydrogens when you're talking about non-bonding, while for bonding, it's much more linear. The electron domain is not as bulky. Now, when we're talking about Vesper theory, when we're talking about geometries, we're not just talking about single bonds, even though that's all we've talked about so far. We might have double and we might have triple bonds, and so we need to think about that. So looking here, if you have a double bond between carbon and oxygen, clearly, if you look, that double bond is pushing the chlorines further down so that the angle between that oxygen and that chlorine, between those bonds, it's 124 rather than being just 120. So clearly the two chlorines are being pushed so that the angle between their bonds is only 111. So clearly a double and a triple bond act kind of like the non-bonding electrons in the sense that they force the atoms around them to compress further to compress their bond angles. And this is because they have a larger electron density, and therefore their electron domain is larger, which forces the chlorines downwards because they are repelling the electrons that are involved with the chlorine bond.